Hello everyone, once again welcoming you all for another video session. In this video session we will be discussing about the basics of transient response in DC circuits. That is, we will discuss what is transient response, what is steady state response, and how the passive elements behave when a DC supply is applied across them. Then finally we will discuss how to convert variables from time domain to frequency domain. Let us start with the objective of this transient analysis. It is used to describe the behavior of voltage or current in a circuit during the transition between two different steady state conditions. So whenever your circuit is containing energy storage elements like inductor and capacitor, the current and voltage, the change of current and voltage will not be instantaneously happening. Instead, there will be a slow variation of current and voltage before those values settle into a steady state. For example, let us consider a three-phase induction motor connected to a three-phase supply using a switch, and let us see the waveform of B phase current using a digital storage oscilloscope. Then compare this definition. The behavior of current between two distinct steady state conditions is explained here. Before the switch is closed or before the switch is turned on, the current flowing through the phase is 0. You can see here the current is 0. Once the switch is turned on, the current suddenly rises to a huge value, and then slowly it is reduced to a normal steady state value. And this part of the current waveform is shown zoomed here. You can see this. There is a huge current, and the magnitude of the current is slowly decreasing and comes back to a normal value. So this is a steady state, and this is another steady state. In between these two steady state there is a transient state. So in this video we will discuss how this transient occurs in a circuit containing inductors and capacitors. Let us discuss some of the definitions. So first one, steady state. So consider a circuit which is a voltage source is connected in series with a resistor. So this circuit is said to be in steady state when the current and voltages do not change with respect to time. You can see here 10 volt source is applied. The value of resistor is 5 ohms, hence the current flowing through the circuit is 2 amps, and the voltage across the resistor is 10 volt. You can see the voltage with versus time. The voltage is constant throughout because I'm not changing this voltage. So a circuit having constant sources is said to be in steady state if the current and voltage do not change with respect to time. Next comes the transient state. So transient occurs when your circuit is containing any one of the energy storage element, either inductor or capacitor. So same DC supply is applied across this RL combination. When the switch is closed, current started to flow through the circuit. Here you can see the current versus time graph. In contrast to the resistor, here the current cannot instantaneously rise to the final value. Instead, it can slowly increase and reaches the final value. So the period during which the current is increasing slowly until it reaches the steady state value is called transient state, and the response of the circuit during this period is called transient response. So a circuit having energy storage elements is said to be in transient state when the current and voltage change with respect to time. After this, the current becomes constant, and hence you will call it as it is a steady state. Next, another definition is forced response. So it is the response produced by the active elements present in the circuit. Consider a voltage source is connected across the parallel combination of resistor and capacitor. And suppose if the switch is closed, this voltage source will circulate a current through the resistor and another current through the capacitor to charge this capacitor. Here the two currents, I can call it as a response, and this voltage across the capacitor also I can call it as a response. This response is because of the current delivered by an active element, which is an external source. So the response caused by an external active element is called forced response. Next is natural response. Consider the same circuit. Suppose if the switch is closed for a long time, the capacitor would have charged to the supply voltage Vx. Now the current will be flowing through the resistor as well as the capacitor. Now open the switch. So what will happen? No more current will be delivered by the voltage source, but the charge or energy stored in the capacitor will be delivering a current through the resistor to get discharged. Now the response, that is current in the circuit, is not because of this source, it is because of the voltage available across the capacitor. Hence the initial condition or the initial voltage available across the capacitor is creating a response through this circuit. It is called natural response. In simple words, if the response is created by an active element or external energy storage, external element, it is called forced response. But if the same response is created by the energy stored in the inductor or capacitor, it is called natural response. Now let us see the behavior of passive elements when it is supplied with DC input. Let us consider a resistor is connected across a DC voltage. So when the switch is open, the current flowing through the resistor is 0. You can see the switch is open, so it is open circuit, and the variation of current with respect to time we can see with the help of a graph. So this is a graph showing the variation of current with respect to time, and this is called time t equal to 0. That is, it is the instant at which the switch is closed, and the time before the switch is closed is called t equal to 0 minus. It means during the switch is in open condition, and after the switch is closed I will call this time as t equal to 0 plus, that is after the switch is closed. Now when the switch is closed at t equal to 0, the current in the resistor rises to I amps instantaneously. The current is rising to a maximum value. See, the switch is closed at t equal to 0. Now you can see the variation of voltage, sudden rise in voltage, instantaneous rise in current, whose value is I. This is how the resistor behaves when you apply a DC voltage. Now let us see how to represent the resistor in time domain and frequency domain, because this will be helpful for analyzing the transients. So a resistor, the voltage across the resistor is V of t, current flowing through the resistor is I of t. So as per Ohm's law, V of t equal to I of t into R. Now if you represent this resistor in S domain, it is I of S and V of S. This equation becomes V of S is equal to I of S into R. Here you can see there is no change in resistance when you convert the time domain into S domain. Now let us see, inductor is connected across a DC supply. So when the switch is open, no current flows through the inductor, that is the current is 0 before the switch is open. When the switch is closed at t equal to 0, the current in the inductor rises slowly and reaches to the steady state value of I amps. You can see here the switch is closed, and you can see here the current is slowly increasing and finally it reaches a steady state value. So compared to resistor, here the variation of current is not instantaneous. So this is happening because of the property of inductor. That is, the inductor does not allow the sudden change of current flowing through it. It can allow only a slow change in the current flowing through it. Here I can separate the transient state and steady state. So the period during which the current is changing is called a transient state. Once it becomes constant, it becomes steady state. Now representing inductor in time domain and S domain, and in the previous videos we have derived the expression for voltage across the inductor. It is equal to V of t equal to L into di of t by dt. This is how it is represented in S domain. The inductor value becomes S into L, and if you take the Laplace transform of this, you will get L into S I of S minus I of 0, where this I of 0 indicates the initial current in the inductor. That means at the instant of closing the switch or opening the switch, if there is any current flowing through this inductor, it is called I of 0, that is initial condition. If there is no initial current, then this term becomes 0. That means the entire term becomes 0. Suppose if there is a possibility of initial current available in the inductor, let us consider there is an initial current flowing through the inductor at the instant of opening or closing the switch. Then in that case, the representation in S domain will have an additional voltage source of value L into I naught. So hence in that case this I of 0 becomes I naught, that is initial current. So this is how you can represent. Please remember these things while deriving the expression and solving problems. These Laplace transforms will help. Next comes the capacitor. Again the same another capacitor is connected across the same DC voltage. Now we will see the variation of voltage with respect to time. So before the switch is closed, that is during t equal to 0 minus, there is no voltage, initial voltage available across the inductor, hence it is 0. You can see the voltage is 0. It is represented with respect to time. When the switch is closed at t equal to 0, the voltage across the capacitor rises slowly and reaches to V volts. It is because the capacitor does not allow sudden change of voltage across it. There will be a slow increase in voltage. Now the switch is closed. You can see the variation of voltage. Like the current in an inductor, the voltage across the capacitor also slowly rising, and finally it reaches the supply voltage Vs. So this slow change is because of the fact that the capacitor does not allow sudden change of voltage across it. There is only a slow change. Again, you can classify transient state and steady state. This is how you can represent the capacitor in S domain and time domain. In the voltage across the capacitor is represented by 1 by C integral I of t dt, where C is the capacitor value. In S domain, when you take Laplace, it becomes 1 by Cs. So Laplace transform of this will give us I of s by Cs plus V of 0 by S, where V of 0 is the initial voltage available across the capacitor. Sometimes if there is no initial voltage, this V of 0 is 0. Suppose there is a possibility that in a circuit, when closing or opening the switch, there is a voltage existing across this capacitor. Let us take the voltage is V0. In that case, the S domain representation will have a voltage source of V0 by S, because this is a constant. When you take Laplace of a constant, it be V0 by S. In that case, this V of 0 becomes V0. So I of s by Cs plus V0 by S. Thanks for watching the video. In the upcoming videos, we will derive the transient current expression or transient voltage expression in RL, RC and RLC circuits fed with DC input. Thank you.